Energy cannot be created or destroyed, rather it transforms from one form to another. Wind turbines are, perhaps, one of the most efficient ways to extract kinetic energy from the wind and to convert it into torque, which is mechanical energy. For this project, we were asked to design a horizontal axis wind turbine that rotated clockwise. The following restraints are given: 3D printed as a single part, had to fit in a box of size 400 by 100 by 150 millimeters, a maximum angular velocity of 3,000 revolutions per minute, and have a bio-inspired original design.
The first decision to make when designing a wind turbine is the number of blades. Usually, an odd number is chosen since it guarantees constant moment of inertia about the vertical axis, reducing the vibrations on the tower. In this case, a two-bladed design was preferred due to the size constraints and to simplify design and manufacturing processes. Once the number of blades is known, it is time to look for an airfoil. The main goal is to find one with a very high lift-over-drag ratio. Having searched through online databases and articles, we finally decided to go for the SG6043. This has an excellent lift-to-drag ratio, was designed specially to be used in small wind turbines at low Reynolds numbers, and it is not overly thin when compared to other high lift-over-drag airfoils, such as the GOI-79 or the E63. Therefore, it met the objectives while still maintaining an acceptable structural performance.
Our design objective is to maximize the diameter of the blade, giving maximum swept area for optimum performance. For this reason, we have decided to put a hinge on our turbine blade to fit a 3D printing constraint. Our first hinge design was inspired by a bad wind morphology, which consists several joints that simulate a flight motion. Due to its complexity in design and time constraint, we have decided to modify the mechanism by retaining only one rotational hinge. This rotational hinge works under clearance feet, which thereby fulfill the design requirement to be printed as one part.
Having decided on the airfoil, the number of blades, and the design idea, the core distribution and the twist of the blade must be determined. In wind turbines, the tips rotate much faster than the roots. The ratio of the tip's velocity to wind velocity is known as TSR. For this project, the TSR would normally be limited by the maximum of 3000 RPM, thus only allowing for TSRs of around 5. In our case, by having a blade with almost twice the diameter, we could make it spin more slowly but still achieve the very high TSR. After reading some academic articles that suggest maximum efficiency happens at TSR of 2 pi, we decided to design the blade for a TSR of 7.
The core distribution is a very complex matter by itself, but it boils down to two different approaches: Betz or Smith's distributions. The former advocates for a continuous increase in chord from tip to root, while Smith's is a more modern distribution which attempts to minimize drag at the root and thus improve efficiency. We decided to use Smith's for this reason. Since tips rotate faster than the roots, their angle of attack with respect to the air decreases, so the blade needs to be twisted towards the direction of rotation to increase it. The best approach to decide the amount of twist is to plot L over D against angle of attack. Then check for the angle of attack that maximizes R over D, and use trigonometry to arrange the blades. The plots and the twist distributions were calculated using the open source software QBlade, which bases its simulations on the well-known X-foil. Finally, since the roots of the blades barely produce any lift, it was decided to go for a cylindrical shape. However, I leave that to my colleague Romain to discuss.
Determining how much the turbine would deform during the test was important to make sure the turbine wouldn't break. To come up with a solution to this problem, we wrote a solver in MATLAB. Solving aeroelastic systems like a turbine blade precisely is difficult. Therefore, we used simplified models for the aerodynamics and structural analysis of the blade. First of all, we made some assumptions about the dynamics of wind turbines. Primarily, we assumed that the behavior of the turbine is independent of the hub, meaning that the hub is rigid and essentially transparent to the air. Secondly, the flow of the turbine can be analyzed independently for each radial section of the turbine. Thirdly, the turbine behaves in perfectly elastic fashion. This leads us to a 2 degree of freedom simple beam model of the blade. Fourth, the material of the blade is fully isotropic. However, the material used to make the blade was strongly anisotropic, which led us to assume the worst possible loading condition everywhere in the blade. Finally, the rotation rate of the blade was taken as constant. From these assumptions, 9 inputs are required. the geometric and aerodynamic properties of the airfoils used, the geometric and physical properties of the blades, and atmospheric conditions. Once the properties of the turbine are set, the structure of the solver must be chosen as well. First, the solver processes some of the inputs into objects and divides the ideal blade into independent sections. Then, these objects are used to assemble a blade element for each section of the blade. Finally, all the blade elements are assembled into a single blade object. We use a simple MATLAB script to conduct operation on that object and assemble the resulting data into human-readable formats. The aerodynamic calculations are done by interpolating lift and drag polars and using a rotating solid disk method for the speed distribution along the blade. The deformations were computed using a first-order implementation of simple beam theory. A centrifugal force correction was then applied as a form of negative buckling load. Finally, the deflected shape, resonant modes, and maximum stress checks were obtained. The solver did not raise any critical issues. The geometry of the root was relatively complex, therefore we used finite element models. These calculations found the stresses to be close to the yield point, but the margin was deemed sufficient.
The manufacturing process began in the Aeronautics workshop with making of the hub for the turbine. First, an aluminium rod was mounted on the lathe and shaped into a cylinder of rough dimensions. It was lathed more precisely, and a hole was drilled in the middle to accommodate the testing rig's shaft. The partially shaped aluminium hub was then placed in a CNC machine and precisely cut into an octagonal shape according to our CAD file. Finally, a keyway slot was punched into the hub. The turbine itself was manufactured on an industrial high-precision 3D printer. The printing process took over 36 hours, and the model was then placed in an ultrasonic bath to dissolve supporting material and allow hinges to rotate.
The turbine and its hub were then assembled and blades fixed in place with bolts. Finally, the turbine was cautiously sanded by hand to reduce surface roughness and then painted with acetone to further smoothen the surface. The result was a smooth and glossy finish. This was done in order to allow our turbine to achieve a better aerodynamic performance during testing. While adding the finishing touches to our turbine, it became apparent that our blades were fragile and flimsy. Although this flexibility had been predicted and could have some positives, seeing it with our own eyes was impressive and slightly worrying. For this reason, we decided to take a very cautious approach. Our priority was to get a reading at 6 meters per second to be safe. The turbine took some time, but eventually self-started with assistance at a wind speed of 10 meters per second. Reaching 6 meters per second was not easy. As predicted by software, 2 modes were encountered on the way there, but the turbine soldiered on. This, however, gave us confidence in our model.
Having reached 6 meters per second, we were finally able to obtain our first power readings, with encouraging results. On our way to 8 meters per second, however, we encountered a very strong mode, and the blade behaved in a very worrying way. The turbine was resisting, but suddenly... So this is how our turbine's life ended brutally. The way our turbine failed remains interesting, and shows the complexity of this entire challenge. The broken root shows that the failure mode is mixed, and that fatigue caused by vibrations played an important role. As a result, it would have been very difficult to predict. However, it is also possible that taking larger safety factors could have prevented such an early failure.
As mentioned earlier, the data taken at 6 meters per second has to be considered the final values for our wind turbine, due to it failing on the way to the 8 meter per second test. However, even with just one test, the power generated was high with a good efficiency. The data recorded can be seen from the table on screen. The TSR is not what we designed for, but this is due to the interpretation of the data from the graphs. As can be seen from the graph, the max power generated is found in a fluctuating regime of the graph at a high angular velocity. This is what causes such a large divergence from the design TSR and was not factored into our original calculations. The main and most obvious improvement is to increase the cross-sectional area of the blades and the root so that the turbine is more structurally sound, and to reduce the deflections caused by the modes. This should allow the turbine to survive past 6 meters per second, and therefore allow for more data to be collected. After all of this, it's easy to say the main thing we have learned through the process is the value of prototyping, and how it would potentially have solved some of the issues that were present for our design if we were able to view a full-size version of the turbine first. Overall, we are proud of the design that we created. We have learnt a lot from this, especially how complicated a wind turbine design is, and how many aspects have to be taken into account.